lecture today is numerical integration, which is basically the opposite of numerical derivative or differentiation. So in the derivative, what we do actually, we try to find the rate of change of the function. Okay, so if the function is increasing or decreasing, we want to know what is the rate of increase of the function. For example, if I want to find the derivative at this point, I want to see what is the rate of increase in this function. Now, on the other hand, the integration actually what it does, if you take the integration of a function that you already took a derivative of it, it goes back to its original state, meaning like the integration cancels the effect of the derivative and vice versa. Okay, so if you have a derivative and you take the integration, you go back to the original function. Now, what is basically or mathematically the integration? When we have a function like this one, and you want to take the integration between points A and B, and how this is how symbolically we represent that. We are finding the area under the curve. This is basically for two-dimensional integration. It is basically we are trying to find the area under the curve. Now, let's take an example from basic physics. If I have a constant acceleration, okay, and we want to go from acceleration to velocity. We mentioned before that if I want to go from velocity to acceleration, we take the derivative, dv by dt. This is basically your acceleration. If I take the integration of both sides, then I will take the velocity. I will find the velocity. So the integration and the derivative at the same time, they will cancel each other, and we will go back to velocity. So the integration of the acceleration is your velocity. So if we see here we have a constant acceleration. It means that the car accelerates at a constant rate. Okay. Now, if at t1 we want to find the area under the curve. Okay. So this is basically the integration. When we integrate v equal to the integration of a of t, you have to set a limit. If we say from 0 to t1, so basically we are trying to find the area under the curve from 0 to t1, and the area here is very clear. If we have a constant acceleration at this rate, 9.8 meter per second, so the area would be the 9.8 times t1, which is this one. So this is the area under the curve. Now, when you want to find the velocity of that, now, so we take the integration. This will be like a number. This is the number. This is 9.8 t1. Okay. Then you go for t2, and you will find at t2. You will find it will be 9.8 times t2, and you will find another point at t3. Same thing. You will find a third area, which is t3. And if you connect the dots, we will have this. And as we know from basic physics, constant acceleration, meaning that the velocity is linearly increasing. Okay, so we can go from the acceleration to the velocity, and the same thing we can go from the velocity to the position. Okay, and as I mentioned, these two things, going from acceleration to velocity to position, or vice versa, very, very important in the concept of autonomous cars, because we want to find one knowing the other. So we use sensors to measure one of the others. Like, for example, GPS coordinate to find the position. If you want to find the velocity, then you take the derivative. If you have a sort of sensor to predict or know the velocity, and you want to find the position, then you take the integration. Okay. So here, this is the area under the curve, which is a triangle. So it is 1/2 t1 times v1. Okay. So you'll find this, and then you will find another area at t2, and so on and so forth. We have the point. This is at t1. This is a T2, and you will have this non or exponential increase, because when you have a velocity that is continuously increasing, so the velocity is increasing with time, it means that the position that you are covering are will be exponentially increasing. Okay, so this is a very short introduction about the need or the relation between integration and derivative. Now, why we need to do numerical integration? We talked about why we need to do numerical derivative before. Here we need to do it for two main things. The first one, there are really some complicated functions. It's very hard to find a closed form solution for them. Like this one, for example. What is the integration for this? This is a bit complicated. So it is better to solve this integration using numerical methods. So this is one reason why we need to do numerical integration when the function is extremely hard to find a closed form solution. Or again, you can find the integration if the relation between two variables is the integral. Like for example, if you are measuring, and we have an example about that, a voltage across an inductor, okay, and then you want to find the current. As we know that here that the voltage is equal to L di by dt. So from this, your di by dt would equal to 1 over LV, or di would equal to 1 over LV dt, or take the integration of both sides. So your I is the 1 over L integration of V dt. So if you are measuring the voltage across an inductor, and you want to find the current, so you will take the integration. So imagine that you are doing this discretely, meaning that you have a voltmeter, and versus time you are measuring the voltage either charging or discharging, and you want to find the current. So you don't have a closed form solution, you have discrete data points. Okay, and this is exactly what we mentioned before in the derivative. This is one of the main incentive to do numerical derivative, is that when we have the function defined as discrete points, not as a closed form formula, this is one practical, very practical application of the integration. Now, how we do the integration, basically, what is the idea? As I mentioned before, that the integration means that you took the area under the curve. Okay, so if we have a curve like this one, so basically, so you try to discretize the area into smaller areas like this one, A1, A2, until AN minus 1. And you go from A to B. So basically, your integration now will be the summation of all of these areas from A1 to AN minus 1. Or you can put it in a simpler or a smaller format. I is the summation from K equal to I, from K equal to 1 to N minus 1, AK, and A is the area, so A1 plus A2, etc. Okay, so this is extremely important. Now the question is, to find these areas, you need to define x1 and y1. These points, you need to define them. Okay, so you know x1, but you don't know x2. So you have to know, sorry, y1. You know x2. You decide that on the x-axis. So then you have to know what is the relation that governs the curve between these 2 points, so that you can estimate or you can find y1, y2, y3, etc. And that will take us to the approximation of the integration, because the integration or the numerical integration is an approximation actually. So we don't find the exact integration, but we try to represent these areas in something that we can calculate. Okay, something, because this function, we don't know this function, but I can approximate this to something that we know, and from that we can find the integration. So for example, this is the simplest way of trying to approximate the area under the curve. So this is the curve, this is your curve, this is the one, this is the curve that we have. Okay, now we don't know this. This is, let's say, this curve, there is no closed form formula for that, and we want to find the integration, let's say from x0 to x4. So what we do here, we try to approximate, we divide this into 1, 2, 3, 4 areas, okay? And we try to approximate each one as rectangular, okay? Now, we have two different ways of doing this. There is one called the upper sum and the lower sum, meaning that between these 2 points, where is the height of the rectangular is the highest point between x0 and x1. So this is the highest point. So this is your y. If you may say, maybe call it y1. Okay, between x1 and x2, this is the highest point, y2. Between x2 and x3, this is the highest point, and so on and so forth. Okay, so we try to here, for example, from x3 to x4, this is the highest point. So this is called the upper sum, or we can do the other way around, the lower sum. The lower sum is that we from x0 to x1, we will see what is the lowest point, and this is the point that we will take care or will decide the height, or will give me y1. Between x1 and x2, we'll try to see what is, when this is hit, where is the lowest point it can hit. It is, of course, this point, because from here to here the curve is increasing, so any other point will be higher than this. So this is the lowest point that we can have. So this is your y2, and so on and so forth. And now when you look to something like this, okay, there is a question here for the x increment. Does it to be the equal? Yes, this is just for demonstration. The increment x, usually we choose it to be equal, although not necessary. However, for the ease of operation, to build the algorithm, as we will see here, the algorithms that we will pick, it is all of them are sort of has constant delta x. Okay, so the summation here will be, or the integration will be the summation from x0 to xn, whatever is xn. Now, clearly that these two, you can just without even doing any numerical analysis or any verification, you can see there is a huge error between the actual value and the approximation. You see, for example, if you use the lower limit, all of these empty areas are error. All of this is an error, because this is a discrepancy between the actual integration and the approximate integration. And also this one, now this is the error here will be in the negative side, meaning that the numerical integration will be much less than the actual. Here it is, on the other hand, you will have all of this like an more, you are, all of these things will be error again, so but it will be in the positive side. So if we can somehow take the average of these two, so between these 2 points, and instead of taking the, assume this is the upper limit and this is the lower limit. So instead of taking the lower limit or the upper limit, I will take the average by taking something like this. So the area will not be a rectangular, but it will be a trapezoid, something like this. So I'm not, I did not approximate this as this area, which will be like very small, or this bigger area, but instead I will take the trapezoidal area and represent my integration. And this is the first way to do the approximation. We call it the trapezoidal rule of integration. Okay. So as I said, I need to know the relationship between the points that we have. Okay, and the trapezoidal rule is based on something called the Newton-Cotes formula that states that if one can approximate the integrand as an nth order polynomial, so this f of x, I can represent it as a certain polynomial, and we know how to do that now. We know that from our background in interpolation. If you have 2 points, I can find the polynomial that represent, and this could be like first order, second order, nth order polynomial. So I can for the integral, I can find the function approximated by certain nth order. Now, if the trapezoidal rule is a special case of this, that we will assume that n is equal to 1. Okay? So we will approximate the area between A and B as a trapezoidal or as a linear function. You can see here between A and B, this is nothing but y equal to a0 plus ax. This is how it is represented. I didn't take any higher order polynomial here. We will see if I take higher order polynomial, we'll have a different approximation. But for the time being, for today's lecture, we will use n equal to 1. N equal to 1 means that I will assume that the relation between, in the curve that I will use it to find the area, is a linear curve between the limits of the integration. So if this is your approximation of f of x, f of x, the function that is in the blue line, I will be approximating it in the red line, which is a linear function, and this can be, the f1 can be represented as such: f of b minus f of a over b minus a. So as you know, this is nothing but the slope m. This is the slope. This is my slope m. Okay, and then this is your x, so this is mx minus a plus f of a. This is to get you the interception, this intersection. That's to find this. Now, just to show that this is nothing but, this is exactly like y equal to a0 plus ax. It's the same curve. Let's calculate this function, f1 at a. If x is a, so if I substitute this as x as an a, so this becomes 0. So f1 of a is a, f of a. If I substitute this as b, okay, so this becomes b minus a. This will cancel. Minus f a plus f a will cancel. So you have it as an f of b. This is just to show you that if I apply the two limits of the line, I will get the right function. So this is the nothing but an equation for a straight line. That's all. Okay. So the integration from a to b of f of x approximately is equal to this. So now my f of x, the blue line, is represented as a straight line equation, which is the red line, and then I will end up having this formula: b minus a times f of a plus f of b over 2, which is nothing but an area of a trapezoid. This is basically the area of a trapezoid. Okay, it is b minus a, which is the x-axis, times f of a, which is this one, plus f of b, which is this one, divided by 2. So that's the area of a trapezoid. Now, if I assume that between a and b I have only one trapezoid, then the integration will be approximated by this formula. But as you can see here, this is really a very, very bad assumption to have this as one trapezoidal. It's much better to have this, represent this as a summation of a smaller trapezoidal, and you can imagine that the smaller the trapezoidal you have, the better or the higher the accuracy you can get, as we will see in the example. So in fact, we don't need to find the expression for f1. Rather, as long as f of a and f of a is known, the integral can be approximated. Yes, of course, you don't need to find the whole idea of the trapezoidal rule or the other rule is to give you the function, the approximation of the function. So you don't need to do any calculation. You need just to substitute. This is the only thing that you need. So here we will derive the formulas, but then when you do the approximation for the integration, all you need to do is just try to use the formula correctly. So now, as I mentioned, it's not really a good idea to have the whole area under the curve as just one trapezoid, but it is much better is to split this into smaller and smaller trapezoids. Okay, so we'll have here this trapezoid, then this trapezoid, and so on and so forth. Okay, so now imagine if this whole thing will be one. So you see the error now between the actual curve and the approximation. This will be the area only. This, so this is the air. This is the difference between the two will be your error only. Okay, so this is the error. Now imagine if your trapezoidal is, you have just one giant trapezoid, which is this one. So you can see the huge, this whole area, and this whole area will be an error. So it is much better to split the area into smaller and smaller trapezoid. Now you need to have this as in segment. And now to answer your question, now for example, if I choose n equal to 1, then your h is b minus a. Now h would be the width of this. Now if n is equal to 2, then you will have two segments. N is the number of segments, okay, and h is the width of that segment or the increment. Okay, so if n is 2, then becomes b minus a over 2, one side, the other side b minus a over 2, n is equal to 4, and so on and so forth. Okay, so this is how you split the integration. Now we need to derive the formula. What will be the formula for that? So now the formula will be the summation of the smaller integral. Now you will have an increment of h. Okay, so each area here will have an increment of h. Each one is h. Okay, and they are equally spaced. So each one is h here. Okay, so you want to take the integration from a to a plus h of this approximate function, plus from a plus h to a plus 2h, and so on and so forth until you reach to b, whatever the relation here. So this is what we are doing here, from a to a plus h to a plus 2h until you reach to the last segment until you reach b. So we start from a to b. This is the whole integration. Okay. Without the need to go through the proof, I will show you the final formula for that. And we will spend some time to understand how to use this formula. So the integration will be b minus a. So we know b. B is the, let me just draw this one here. So this is my function. So this is my a, and this is my b. So a and b is the lower and upper limit. So we know b and a. What is n? N is the number of segments. Could be 1, could be 2, could be 4. So we take them as multiplication of 2, 2, 4, 8, 16, etc. Okay. So this is your a. So this is your n. How many? And this is, you decide how many n you want to use. Then f of a and f of b, this is known to us. So this is your f of a, and this is your f of b. So this is also given to us. So now we know b, a, n, f of a, and of b. Now we are left with this summation. It goes from I equal to 1 to n minus 1. N, as I said, number of segment. If n is equal to 5, sorry, it is 4. So this goes from 1 to 3. So you have 3 elements at I equal to 1, 2, and 3. And here is the function. You calculate f from a, which is this, to I plus h. Okay, h we already calculated that. This is the h. H is b minus a over n. So which is the increment width. So we know h, and I is the counter that we use in the summation. Okay, so now everything is clear. Now let's assume that n is equal to 1. Okay, so what do we have here? If n is equal to 1, this becomes b minus a over 2 times f of a. Now this is goes from 1 to n minus 1. So this becomes 1 minus 1, which is 0. So I don't have any item here from 1 to 0. Then I don't have any item plus f of b, which is the same formula we had it if n is equal to 1. So this is the more general formula that we will be using to find the integration for all n's that we will assume. Now I think we are ready to have two examples. We will this will be until the end of our lecture today. So this is a curve, exponential function. This could be like a charging of a capacitor, starting with an initial charge as V equal to, it has initial voltage, and then we start to charge the capacitor for a certain time, okay? So I want to take the integration from x equal to 0 to x equal to 10. And using 1, 2, and 4 segments. So n will equal to 1, n equal to 2, and equal to 4. So n equal to 1, so this whole area will be one trapezoid, the whole thing. Okay, so this whole, so you expect clearly that the trapezoid will have like a significant error, and the function will be, or the approximation will be higher than the actual, and we will verify this. Now then we will have 2, n equal to 2, so this is at 5. I will have one trapezoidal here, another trapezoidal here. You can see that there will be like a significant reduction in the error as we move on. So let's start. So we'll start here with n equal to 1. Okay, so I want to find the integration of a to b f of x d of x. Now we said that this would be approximated by b minus a. Now we will use n equal to 1, so the whole area will be one trapezoidal, and f of a plus f of b divided by 2. Now we know a is equal to, we want to find the integration, let's go back here, from 0 to 10. So a equal to 0, b equal to 10. Now I need to find f of 0, which is e to the power of 0 over 5, which is equal to 1. And f of 10 will equal to e to the power of 10 divided by 5, which is equal to 7.39. So this is the f of 0 and f of 10. So let's go back here to the integration from 0 to 10 of f of x dx. And now f of x is nothing but e to the power of x over 5. This is your f of x. This is approximated by 10 minus 0, f of 10, sorry, f of 0 plus f, doesn't really matter because you can have f 0 plus f of 10 or f 10 plus f of 0 divided by 2. So we have everything here. So we do the calculation. This is equal to 41.9095. So this is when n is equal to 1. Now, let's move on. And this now go for n equal to 2. Okay. Now we have to define h, which is the increment width. H is equal to b minus a divided by n. B is 10, a is 0, the limits, over n is n equal to 2. So h is equal to 5, and this makes sense because you want to make n equal to 2 segments. So, and I have the limit for 10, then each one has to be 5. So this makes sense. Now the integration from a to b of f of x d of x. Now we will use the general formula, which is b minus a divided by 2n multiplication of f of a plus 2 summation. I will write the general formula and then we'll substitute. I equal to 1 to n minus 1 f of a plus I h plus f of b. This is the general formula. Let's substitute now. So this is approximated. So this is approximated equal to b is 10, a is 0, n is 2 times 2 over 2. F of a, f of 0 plus 2 summation of I goes from 1. This is 2 from 1 to 1. So we have only one element here. F of a is 0 plus I, this is I, and h is equal to 5. Okay, so that's it. Plus f of b is f of 10. So this is approximately equal to, this is 10 over 4. F of 0, we know it from the previous calculation, plus 2. This is becomes I equal to 1. So this becomes f of 5 plus f of 10. So this is the formula. Now we know everything except f of 5. We need to find f of 5. There's nothing. F of 5 is equal to e to the power x of 5 over 5. And this is equal to 2.72. Okay. So now we will substitute here. You will find this is equal to 34.575. So this is goes from 41.95, and as I have shown to you in the graph, that this is looks very close, would be very close to the actual answer compared to this one, much closer than this one, because this is, looks like the error is huge. Okay, now let's go for the last one with n is equal to 4. Okay, so here n is equal to 4. Now again, I will define h. h is equal to 10 minus 0 divided by 4, which is 2.5. Again, this makes sense. I have total length of 10. Okay. Now I will have h. I need to have 4 segments. So each h will be 2.5. This makes a lot of sense. Okay. So your I, the integration, which is goes from 0 to 10. Sorry. So this is equal to the function f of x, d of x is approximately equal to, again, we have the total formula b minus a over 2n f of a plus 2 summation I goes from 1 to n minus 1 f of a plus I h plus f of b. This is the general formula. Okay, so let's substitute here. B again 10 minus a is 0, 2 times 4, because now n is 4. F of 0 plus 2, I goes from 1 to n minus 1, n is 4 to 3. So we'll have here I equal to 1, 2, 3. We will have 3 elements. F of a is 0 plus I, which is this, times h. h is 2.5 plus f of 10. So let me open this more. This becomes 10 over 8 f of 0 plus 2. Now I equal to 1, so this is f of 2.5 plus I equal to 2, f of 5 plus I equal to 3, f of 7.5 plus f of 10. Now if you do this, you will find this is equal to 31.46. now you start to see that the increment or the change that happened in the function will go smaller and smaller. Okay, which is we expect that because now we are increasing the number of segments. Okay. Now this is the summary. When n equal to 1, n equal to 2, n equal to 4. So this is the integration value, and we calculate the absolute exact relative error. This is the actual value when you do the integration. Okay, this is the actual value. So you will find that the error, as you can see here, is going down every time we will increase. It goes by 25% almost. Okay. Now, how to approximate the error in the function? We will learn about that. We don't need to find the actual solution to have an idea about how much will be the error. Okay. Let's move to the second example, which is now this example we have a continuous function. Okay, so we did the integration of a continuous function. Now, in this example, we will do the integration for discrete values, which is this is the two possibilities. Either I give you a continuous function or discrete values like this. Okay, so here I have a voltmeter that measures the voltage across an inductor. And this is the timestamps, which is the independent variables. And here is the voltage that is goes for 10, 5, 0. So these are the values of the voltage. Now the initial current is giving us 2 amps. So there was 2 amp initial current. I want to find the current after 4 seconds using 1 and 2 segments in the integration. So I have discrete values, and I want to use n equal to 1, n equal to 2, and then we want to see the error between having this. Now, I don't know the exact value here because I don't know the exact function. I can approximate the function, it's a different story, but now assume I'm just having discrete data. So now I will be working on a relative approximate error because I will be comparing 2 iterations together, not with the exact. In the previous example, I'm comparing it with the exact value that I know. Here, I don't know the exact value. Okay, so here this is the n equal to 1, so this is the function. Okay, and I will have, goes from 0 to 4. So this is your A, this is your B, this is your f of A, and this is your f of B. Okay, so now we have everything. Okay, now before just so this is your n equal to 1. We know that I, the current, is equal to nothing but 1 over L, the integration from the 0 to the t of the voltage, V dt, plus the initial condition, I of 0. Okay, so let's just take this out and find this out first, and then we will substitute in the full formula. So I need to take from 0 to t, V dt. Okay, so this is approximately equal to what? Equal to t. So this becomes B minus A. This is your B, and this is your A. So it becomes 4 minus 0 times f of A. This is your f of A. So it becomes 10 plus f of B, which is minus 30 divided by 2. Okay, so this is equal to minus 40. Now, if I come and substitute here to find the current, I is equal to 1 over L is 1/2 times minus 40 and plus 2, the initial condition. This will give you minus 18 amps. Okay, very good. So now let's move to n equal to 2. Now, again, we use exactly the same general formula now. H now, my H will be, so n is equal to 2, so I have to have 2 segment. My h will become equal to 4 minus 0 divided by n, which is 2, so this is my h is equal to 2. Okay. Now again, I will find the integration of 0 to t v dt, and then I will substitute in the total formula. So this becomes b minus a, 4, this is your b again, and this is your a, this is your f of a, and this is your f of b. Okay, so this becomes b minus a, which is again 4 minus 0 divided by 2n. This is your n, so this is 2 times 2, f of 0 plus 2 summation I goes from 1 to n minus 1. n minus 1, n is 2 to 1. F of a is 0 plus I times h. h is 2. Plus f of 4. So this becomes 4 over 4, which is 1. F of a plus 2. And this becomes f of 2 plus f of 4. And if you do the calculation, you will find this is equal minus 40. Then your current I is equal to 1/2 minus 40 plus 2, again minus 18 amps. So if I use I equal to 1 or I equal to 2, in both cases, I will get the same answer. What does this mean? What does it mean if my approximation both have this? Until you think about this, let me see here. Can I use a calculator to evaluate the summation all at once? Yes, you can use a calculator for this one. As far as use the formula, how to calculate this summation, you can use a calculator. Yes, it is linear because it is linear. This is why it is this the same. So when you look here to the, when we draw the answer here, you see this is a linear function. Okay, so since it's a linear function, so if you want to approximate this as a trapezoid, then this the area under the curve will be like this. So this is the area, there will be the area under the curve. So this is like this. Okay, so the area under the curve will be like minus 20, and this is why it doesn't really matter if I have it as 2 areas, because the actual line and the curve are matching because the relation is linear, and we are using a linear function to model a linear function, then we will have no error. So if I increase the number of segments, that will not really lead to any improvement in the calculation.